Hi guys, we're looking at our second lab here called Measuring Depths. It's using an echo sound reader. So first I'm gonna go through the directions and I'm gonna read everything with you. And then you are going to work on it on your own. Okay, this lab should take 2 days, especially if you actually watch the video and follow directions. So don't expect to be finished just in one period. Okay. Um, Although you could continue to work on it, it would probably take you about an hour from start to finish. So really it's a 2-period lab. Okay. All right. So taking a look, we are going to get an in-depth look at ocean instruments that use sound to measure water depth and create seafloor images. Then we're going to determine the depth of the seafloor from echo sound data, and we're going to create a depth profile from that completed data. I have the echo sounding data for you. You're going to calculate that, so you will need a calculator. And then graph paper. I have graph paper on this, and I'm also going to show you how to just do it completely on the computer while we're doing the directions here, so that you don't need to print your lab and graph it. Some of you might want to, because sometimes doing it on the computer can be a little bit annoying, but you don't need to do it. So background information. People have always been curious about the land beneath the sea, but until relatively recently, that realm of 10,000 meters or 6.2 miles below the surface was virtually unknown because its impenetrable watery mantle. Scientists make bathymetry or ocean depth charts of the ocean basins for the same reason we send a space probe to map Mars. Surface structure and shape of the planet belies the formational processes and geological events that shape the seafloor. If not for mapping the seafloor, we might still be debating whether plate tectonics is fact or fantasy. So, weighty attempts. Early sailors needed to know ocean depths, particularly along coastlines and near harbors, so that their ships would not run aground. Ocean depths were measured with a weight on a line, and the depth measurements were limited to shallow water by the lengths of the line carried on board and the enthusiasm of the captain for making the soundings. Not until the 1870s, during the famous Challenger expedition, were deep soundings routinely made. But technique was the same, laboriously lowering a weight on a rope and trying to figure out when it hit bottom. This technique was arduous. Arduous means difficult in deep water, and the results were seldom accurate for 2 reasons. 1, strong currents might pull the rope and the weight to the side, and 2, the length of the rope needed to reach the seafloor this was so heavy it was difficult to tell whether the weight actually hit the bottom. Many people assume that it was the development of scuba and submersibles in this century that allowed the ocean's floor to be explored. However, scuba divers are typically limited to the upper 2% of ocean depths because of water pressure. Beneath the upper few hundred meters, all the sun's light is gone, and although the submersibles have headlights, observers inside can only see a few tens of meters because particles in the water scatter the light. Groping around to the deep sea floor in a submersible is akin to walking around on a black, foggy night with nothing except a flashlight. One can only get a dim perception of the total picture that surrounds the sub. So the echo sounder. What really opened scientists' eyes to the deeps was the invention of the echo sounder. Originally developed to detect enemy submarines before World War II, the echo sounder is just sonar, or an acronym for sound, navigation, and ranging, put to geologic use. Here's how it works. So focus now, guys, because this will help you understand how to calculate those numbers. So a transducer, typically on the bottom of the ship's hull, emits a short sound pulse. The pulse travels downward, strikes the seafloor, and returns to the transducer. The echo sounder times the return of that original signal from the bottom. Because we know the speed of sound in water, which is about 1,500 meters per second, that round trip time can be used to calculate depth. And it makes sense, guys. If we know how fast it's going, right, and we know how long it takes, then we can figure out how far it was. With the echo sounder, scientists can measure the ocean depth in a matter of seconds while the ship is moving. An improvement on the ropes and weights technique, which took off which took hours stopped in the ocean. The echo sounder enables the ships to routinely make thousands of depth measurements while crossing the oceans, and it became possible to make modern bathymetry or ocean depth charts. Many ships carry echo sounders or precision depth recorders that instantly display the depth of the sea on a computer screen. In fact, you can buy one of these at your local hardware store for finding fish at the lake. All right, I'm going to take here. Profiling the seafloor. When a recorder plots successive echo sounder pings, it produces an acoustic picture of the sea bottom and shows the thickness and geometry of the sediments. This technique is called seismic profiling and is practiced in its most advanced form by oil companies who search offshore sediments for hydrocarbons. Hydrocarbons are a type of oil. Right? All oil and gasoline and things like that are hydrocarbons. To explore deep within the sedimentary wedges surrounding the continents, oil companies use explosive sound waves, air guns that make a pop sound with compressed air, to generate low-frequency sound waves, because lower frequency waves penetrate further beneath the sea floor. When a sound pulse echoes from the sea floor, typically some fraction of the energy is transmitted into the sediments beneath the sea bottom. These waves reflect off horizons between sedimentary layers, where physical properties change slightly, and returning signals tell the thickness and geometry of the sediments. The returning sound waves are received by long arrays of listening devices called hydrophones that stretch 2 kilometers in length. In a process called 3D seismics, data are collected in such a dense grid that computers can treat the reflections as a volume rather than a profile, so the analyst can look at the data from many different angles in 3 dimensions. Three-dimensional seismic data are hideously expensive to gather, about $1 million for 30 square kilometers, and are jealously guarded by the companies that spent so much money to acquire them. So such data have not had a huge impact on mapping the sea bottom. If oceanographers are not interested in deep imaging sediments, they can use 2 other acoustic techniques that allow more rapid exploration of the seafloor at less expense. This is multi-beam echo sounders and a side scan sonar. So a multi-beam echo sounder is an improvement on the conventional echo sounder. Instead of calculating a single depth value for the spot beneath a ship, a multi-beam echo sounder can determine the wide profile of depth in a line perpendicular to the ship's direction of travel. And when it says see the top diagram, it really is referring to this one over here. When the results of many deep soundings from a moving ship are collected, as illustrated in the lower diagram, this should be the lower diagram, a swap of depth values along the ship's track. A multi-beam echo sounder uses 2 series of transducers that send or receive beams of sound. The transmitting transducer emits an upside-down fan-shaped pulse of sound. The sound bounces off the seafloor, then returns to the receiving transducer, which calculates distance to the seafloor from each point along the outer edge of the fan. Typically, a multi-beam echo sounder calculates about 60 depth values in each cross-track profile, and the bathymetry data is 2 to 3 times the water depth. By collecting a grid of such swaths, a detailed 3D map of the bottom can be constructed. Will we ever have a complete map of the seafloor? Although you would think that multi-beam echo sounders and side-scan sonars would have allowed scientists to map most of the ocean basins by now, this sadly hasn't happened. The problem is mainly that the oceans are just plain big. Multi-beam mapping a ship moving at 10 knots or about 11.5 miles per hour in 3,000 meters of water can cover 111 square kilometers in an hour. But oceans have an area of 3.6 times 10 to the 8th square kilometers, implying that it would take the ship on the order of 371 years to finish the job. Ouch. Academic scientists collect data to learn about how the seafloor has got to be the way it is. Many more industry oceanographers just need to know the depths and shape. The offshore high-resolution seafloor mapping industry is booming because of the need to emplace oil rigs, build pipelines, lay fiber optic cables, map harbor entrances, and dredge waterways. Okay, so now we're going to start doing our calculations. So we have to complete this data table. This is the echo sounding data from an area near Iceland. Echo sounders compute the ocean's depth based upon the return time of a pulse of sound. Complete the following data table using the known value of the speed of sound through water, which is 1,500 meters per second. Okay, so we are going to use the 1,500 meters per second, and then we know the time it traveled, and we're going to get the depth. We're going to get the distance it traveled. Okay, so in order to figure this out, right, we're going to look here. The speed of sound is 1,500 meters per second, so you're going to use a proportion to find the missing values, okay? So we're going to separate meters per second, so 1,500 meters over 1 second, okay, is going to equal x, because we don't know how many meters, right, and that would be our distance there, over negative 1.37 seconds. Now, the negative is really only there because we're going to get negative values for our depth, and I'm going to explain that in a little bit. To get our answer here, we're going to cross multiply, and we're going to find that 1,500 multiplied by 1.73 will give us our answer, which is x. So it's negative 2,600 meters, okay? So that's here. So to find the next answer here, guys, you're going to do the same math, but instead of 1.73, you're going to put in negative 1.47, right? So end up multiplying that 1.47 by the 1,500 meters, and that's how you get your x. All right. Now here, you're going to have to figure out the travel time. You have the depth. So just plug in the numbers differently, okay? So you have, when you do this one, this is going to be you put 2,900 in place of x, and then you're going to move the x down here and still cross multiply, okay? It should, when you get a number, it should make sense, meaning it should be in between negative 1.33 and negative 2.33, okay? And that's how you know you got the right answer, okay? So once you have your data in place, you're going to be making a bathymetry chart or the ocean depth chart. To do that, you have to graph the distance from the start. Okay, here's your distance, and then versus your depth, and that's going to give you a profile. Okay, so as it says, to graph the seafloor, you're going to determine an appropriate scale for each axis. Let's quickly take a look at that. Okay. You guys will see that the shallowest part, right, is you're going to go from 0. So the depth you're going to start at 0. And then you're going to look at the deepest part, okay? The deepest part is going to be almost, it's like this number. I think it comes to 35. Hold on one second. Let me just. Yes, when you get that deepest number, it's almost 3,500 meters. Okay, so 3,500 meters, and so from 0 to 35. So when I look at my graph, and I'm going to show you guys how to do this in a second on the computer without printing it. But this is really important you pay attention to, because this is always messing up kids. If you're going to be doing depth of 0 is the surface water. So that's why the numbers are negative, and that's the only reason they're negative, is because you're going to start at 0 and then you're going to go down. Okay, right? So you're going to want to count the boxes, and if I did it right, there should be 35 boxes. Okay, so you should be able to start 0 here and end up at 3,500 here by making every box worth 100. Right? Count the boxes. Okay. Now the next thing you're going to be looking at is horizontal distance, which is over here. So again, you're going to go from 0 to about 800, right? So there should be 40 boxes here, okay? So every box can equal 50. So you're going to start 0 over here. Now you don't need to label every box, guys. You can skip a couple lines. So if every box is 50, every 2 boxes is 100. So every 4 boxes would be 200. So I can just start by writing 200 and then counting to 4 and then doing 400. All right, and this way you're not crowding it with numbers. You can put your distance if you want down here if it makes more sense. But remember, your depth is going to be here. It's going to start at 0 and then it's going to go down. And when you graph it, you're going to end up getting a line. Okay, that shows what the ocean floor looks like. Now to graph it on here. okay? You're going to click this. Of course, now it's not letting me. That's fun. All right, you're going to click this, and then you're going to go to edit. And it's going to bring you to a Google Drawing where this is here, okay? And this is far from perfect. Your graphs will not be perfect. I am okay with that. You're learning a new skill and you're graphing at the same time. So you're going to have to put text boxes in and label them. And remember I was saying before, you don't have to label every line. Well, thank God you don't have to label every line because it's going to get really a little crowded. So there's my 0. I'm going to make my 0 because my depth, I'm going to put my depth here. And so I'm going to try to make it look like my 0 is right next to this line, okay? And then if every box here, I think we said 3,500, so I think every box is supposed to be 100. Well, if I want to just label, 500, 1,000, I can do that. So I'm going to go down 5 lines here. So 1, 2, 3, 4, 5. And I'm going to put another text box, okay? And I type my 500. Then I'm going to make sure it lines up with the right line. Remember, it's supposed to line up with this line right here. And it pretty much does. So if I click off of it, you can tell this line right here is supposed to be 500. All right. I'm going to repeat myself here. It's not going to be perfect. Do the best you can, okay? Don't ever forget to label, right, your axes. So over here, it's going to be the depth in meters, right? Okay. That looks good enough. I'm going to continue my lines. Once you get your lines and you're going to do your horizontal distance over here, okay? Once you do that, and again, don't try to label every line. Skip a couple to space it out so you can actually read your numbers. You're then going to, and this will be difficult, but you guys can do this. You're going to put lines. Let's say I wanted to graph from here to here. Okay, great. If I want to change the color of my line, I can, right? So I can see it. And then I'm going to add another one. From here to here, right? From here to here. So this isn't bad. It's not perfect, but it's definitely doable. Oh, I just made a mistake. They have great undo arrows here, so you can use those. And yeah, so you guys should be able to edit it. And then when I save and close, it's going to show up my graph and it's going to put it in the same area. If I want it to be, I have a little space down here, so I can make it go a little bit like that. And it's all there and my numbers are there and they don't look that bad. Don't forget to add a title, okay? And I'm going to let you guys determine what the title should be, but all titles should always be the effect of the independent variable on the dependent variable. And your independent variable is always going to be on your left side and your dependent variable is always going to be the right side. So I want you guys to write the title, but I kind of told you how to do it. If you look, again, the depth is here, okay? So this is how you're going to set it up like this. You're going to start at 0 and go down, okay? And your horizontal distance is here, okay? And you guys should know how to graph. I'm sure that you do. And then I already told you the speed of sound in water. It says check the article. It's just saying go back into that reading that I read you. And then you're going to answer these questions and then you're done, right? So I figure you guys, if you watched the whole video, hold on 1 second, I clicked the wrong thing. If you guys are watching this whole video, you're at about almost 20 minutes before you even start. So if I were you today, for your lesson today, I would just go on and calculate the numbers on the graph. And then I'd be done because that might take you the rest of class time, right? And then tomorrow I would graph it, which could seem really easy, but it might take you guys a little while, especially if you're learning how to use that drawing tool and editing it and first time you've done it. And then you're going to answer these questions, okay? And I'm going to make them so they're text boxes, so you guys just have to type in there. All right? Okay, if you guys have any trouble, don't forget to come on to the extra help every day. I have the Zoom link up on Classroom. That is a recurring Zoom meeting. I will be on at 1:50. All right, have a good day, guys.